Consider the expression log 2 of x plus log 2 of x. Based on our new rule, we can simplify this expression as log 2 of x times x, or x squared. On the other hand, if we add something to itself, like a plus a, or m plus m, those things can be simplified as 2a. In this case, 2 log 2 of x. And now just ignore the middle and look at the two ends. These two are equal. Next, we're going to go 3 times. So when we have 3 of such expression added, very similarly, one side is log 2 of x cubed. On the other hand, if we add something to itself 3 times, like a plus a, that can be simplified as 3a. So in this case, this is 3 log 2 of x. And again, ignore the middle, compare the ends. These two are equal to each other. So this can continue, and we would have n times log 2 of x added to itself. We would have log 2 of x added to itself n times. And therefore, this side would be n times log 2 of x. But also, if we apply this new rule repeatedly, then we're going to get log 2 of x to the nth power on the other side. So our new rule is that log 2 of x to the n equals to n times log 2 of x. Well, actually, when we state this new rule in its full generality with a, b, and c, then we no longer seem to assume that this reflects repeated addition. Our argument only works for positive integers, but this rule is true for all kinds of real numbers, and there is a rigorous proof for that. We're going to use this third rule of exponents. Proof is going to be very similar to the previous two proofs. We're going to compare a to the left-hand side and a to the right-hand side. With surprise, we will find that they are the same, and if two a powers are equal, then the exponents themselves must be equal to each other. A to the log a of b to the power of c, well, that's just b to the power of c. The other side, a to the c times log a of b, well, we would like to simplify a to the log a of b, but c is kind of in the way. We would like to match a with the log a, but we can't yet because the c is bothering us. So let's get rid of that. Now we're going to use this rule where if you have a multiplication in the exponent, you can interpret it as repeated exponentiation. So we're going to rewrite this as a to the first, the log a of b, and when we're done, to the c. And when simplify the expression inside the parentheses, we just get b to the c power. So there it is. Two a powers are equal to each other. Therefore, the exponents themselves must be equal to each other. We might ask, do we have that annoying asterisk thing that this rule is only valid when both sides exist, and that's not the same for the left-hand side and the right-hand side? Unfortunately, the answer is yes. Consider, for example, log 3 of minus 3 squared, and, well, I shouldn't say equal yet, and 2 times log 3 negative 3. Are they equal? They would if they both existed, but the right-hand side does not exist because the logarithm of a negative number is undefined, and that stays the same way even if you double it. This side is okay because negative 3 is first squared, so it becomes positive 9, and that has a logarithm. So in this case, this is undefined, and this is 2. We see a similar situation as before. The two sides don't have the same domain. The left-hand side is the more generous one in this case, because b could be negative, but if c is even, then we kind of get away with it. That will not happen on the right-hand side. So this means whenever we make this step from here to here, we must check at the end. This was a non-equivalent step, which means we were taking the risk of obtaining extraneous solutions that are solutions maybe of the last equation, but not of the first. This newly found identity is very useful because if you notice, this will allow us to sort of drag things down from the exponents. We're going to soon see exponential equations in which unknowns are often in the exponent, and then taking a logarithm would be one way to shake them down to the baseline. Let's see an example. Suppose we have a quantity 250, and what happens to this quantity is that it's going to increase by 30% in every month. How long does it take for this quantity to reach 1 million? The quickest way to increase a quantity by 30% is to multiply it by 1.3, which represents 130%. Once that happens, the next month, this quantity will get multiplied by 1.3. And then the next month, the result of that will get multiplied by 1.3. So in X many months, it's going to get increased by 30% exactly X many times. What is the value of X so that this quantity grows up to be 1,000,000? So this is an exponential equation. One thing that we can easily do is isolate the exponential expression. So we're going to divide both sides by 250, 4,000. And now what we're looking at is a very simple basic exponential equation. And we know that if we have such an expression, we can just rephrase it as a logarithmic statement, and that would be the solution, because x is the exponent that we need on the top of 1.3 so that we could achieve the product that is 4,000. That is the exact value. So far it was reasonable to stop here, but I think in this particular case we would like to know a little bit more in detail. Is that 2 years? Is it 20 years? How many months is that? So we would like to have an approximate value of this expression, but our calculator does not have logarithm with the base 1.3 programmed into it. What it does have is the base 10 logarithm, which we call the common logarithm, and the natural logarithm, which has base e. Instead of going for the exact value this way, we can just take the common logarithm of both sides. Why would we want to do that? Well, because of our new rule, this x will fall off and becomes a multiplier. We just have to solve for x. So x is log of 4,000 divided by log of 1.3. So we got a decimal as an approximate value. That means that under these conditions, it would take a little bit more than 31.5 months to reach 1,000,000. Well, you might ask, well, what if we did the same thing, but we chose the other logarithm? What if we went, well, let's take natural logarithm of both sides. As you see, the computation is identical. And yes, ln of 4,000 does not equal to log of 4,000. And the same can be said about ln of 1.3 and log of 1.3, but the quotient is the same. By the way, before we move on, how could we check our answer? In practical terms, we could see what happens if we compute this expression using 31 and 32. One should be too small, the other one should be too large. So let's check that out. 250 times 1.3 to the, let's go for the too big, 32. That's too big. And when x is 31, then it's below. So it very much looks like our answer is correct. But something is going on here. It looks like that this rule enabled us to find approximate value of logarithms that we couldn't until now. Maybe this is something that we can do in general. Let's check out, say, log 3 of 7. Now, we know that log 3 of 7 is a number between 1 and 2, because 3 to the 1 power is 3, too small, and 3 to the second power is 9, too large. So it's somewhere in between. Let's just call it x for now. And let's rephrase the logarithmic statement as an exponential statement. So 3 to the x must be 7, right? X is the exponent that we need on the top of 3, so the resulting product is 7. And now we can take the natural or common logarithm of both sides. The reason we did that, because now x falls off using this new rule of ours. And we get that x is log 7 over log 3, which is just as exact as log 3 of 7, but this one we can punch in the calculator. So if we want an approximate value, we get. Did we have to use the common logarithm? Could we have used the natural logarithm? As a matter of fact, we can use any logarithm. So in its full generality, well, we're going to still play with log 3 of 7. Log 3 of 7, if we call it x, and rephrase it so that we have the exponential statement. And now we can take any logarithm of both sides. Let's take log a of both sides. X falls off, becomes a multiplier, and we can solve for x. What we have is that log 3 of 7 equals to log a of 7 divided by log a. This formula has a name. It's called the change base formula, because this is how we change the base of a logarithm. In this particular case, we switched from base 3 to base a. This formula is kind of visually nice. It's easy to remember because here in the original logarithm 7 was visually above 3, and in the other side also 7 is visually above 3. So it's relatively easy to remember. What kind of logarithms would we want to change to? That always depends on the problem. For example, with log 3 of 7, it's reasonable to choose the common logarithm because it's in the calculator and we have instincts to think of numbers in terms of 10 powers. We could also use the natural logarithm, which in our next course, calculus, we will see why it has its advantages. But we can also use 7 as a new base. So what would happen if we switched base? Instead of deriving it, let's state log A of B is the same as log C over log C, and now visually above B, visually below A. Right. Log 7 of 7 is 1 divided by log 7 of 3. We have already proven it in several different ways that when you swap two numbers in a logarithm, you get the reciprocal quantity. There are going to be problems that hinge on finding just the right base to switch to. Do we have that annoying thing we're getting used to when both sides exist? Let's investigate that. For generality, here is the change base formula. So the question is, do these two expressions have the same domain? For the left-hand side, A has to be positive, B has to be positive, and A cannot be 1. For the right-hand side, we must have picked C suitable as a base of a logarithm, which means positive and not 1. A must be positive, B must be positive. But notice that there is a little discrepancy because it doesn't say A is not 1. But what would happen if A was 1? If A is 1, then on the right-hand side, the denominator is 0. Log C of 1 is always 0. So actually, the right-hand side has the same domain as the left-hand side. So we finally lost that discrepancy between the domains of two sides. This is actually perfect.